Welcome to the third lecture. So, let us recall what we have observed in the last lecture. So, first of all, if I have surface patches sigma from U to R3 and I have another open set U tilde and we have a bijective smooth map with smooth inverse then phi tilde equal to phi compose phi sigma compose phi is a reparameterization of sigma u. This was the first observation we make. We did not prove it. As I said, the proof will be posted. And the second observation was that about the transition maps. That I have a surface S in R3 which is regular and smooth. We will always be dealing with regular and smooth surfaces. I have sigma from U to S intersection W. You can look back at the definition of the first lecture. And sigma tilde from, let us say, U tilde to S intersection W tilde. Then I have this map phi which is from sigma inverse compose sigma tilde from V tilde to V, where V is this sigma inverse of S intersection W tilde, V tilde is sigma tilde inverse S intersection W tilde. So, this map is transition map which is smooth, bijective with smooth inverse. By these two observations, we have decided that properties of smooth surfaces are modulo reparameterization. So, whatever property we will define for the surfaces in R3 is up to reparameterization. So, it should be true under reparameterization. So, with that idea, let us define smooth maps between surfaces. As usual, I start with an example. My example is, first example is wrapping the plane onto a cylinder smoothly. So, I take this cylinder, this is my z axis, so this is a cylinder, radius 1. Okay. and I take the plane. So, this is S. So, this is the surface of the cylinder. I take the plane P is a YZ plane with not the entire YZ plane, but with 2 pi. Now, what I am doing here, I have the cylinder, I have the plane out here. I am trying to wrap the plane onto the cylinder smoothly. Now, as you know, or you can see very easily, S can be parameterized by a single surface patch, that is cos u, sin u, V, right. A typical point on cylinder is, this is the height V, and this is the angle u. Maybe I draw it a little bit carefully. So, a point here, this is the height V and the angle u. So, this point can be uniquely determined by cos u, sin u and the height V. Now, how this YZ plane is parameterized? YZ plane is parameterized by sigma tilde uv is 0 uv. Now, if I try to wrap it, what will happen? So, you immediately understand that this point will go to, so this particular point, which is at angle u with YZ plane, that will be mapped into this point, and according to, so V is between 0 to 2 pi, and that will, the B coordinate will be mapped to the height of the point. So, I can define the map f of, maybe I will write here, or okay, let me write on the board itself. F from f of 0 uv is cos u sin u v. You can check this f is a smooth map in the sense that all its partial derivative exist and continuous, all partial derivatives of all order exist and continuous. Actually, f inverse also exists, and this f is actually a so called diffeomorphism. What is the diffeomorphism? It is a homeomorphism with which is smooth, that means all its partial derivative exist, partial derivative all order exist. So, we will try to remember this example, that such a way you can generate smooth mass between surfaces. So, in general, while defining, let us make things little formal, that suppose I have surfaces S1 and S2, regular smooth surfaces, so I have a map from F from S1 to S2, assume S1 is covered by, okay, let us say sigma 1, a single surface patch, does not matter, otherwise we can always go back locally, and S2 is covered by, and sigma 2 . So, these are surface patches. Then I have a map sigma 2 inverse compose F compose sigma 1. Sigma 1 takes U1 to S1, F takes S1 to S2, sigma 2 inverse takes S2 to U2. So, this is from U1 to U2. So, we will say F is smooth if this map is smooth. For example, here I have the plane P S1, my other surface S2 is the surface of cylinder. This F is smooth, then provided sigma tilde inverse F compose sigma is smooth, but here it is trivial map F itself. So, this is an example of a smooth map. So, this definition is invariant under reparameterization. That is the way we have done it, right? Come to think about it, if I have just S1 and S2 are same, then under reparameterization map will be smooth if for every reparameterization sigma 1 and sigma 2 it will be smooth. I mean, to illustrate this point, maybe we will look at sigma 1 from U1 to S1, sigma 2 from U2 to S2, sigma 1 tilde, sigma 2 tilde, U1 tilde, U2 tilde, reparameterization of whatever we have done in the earlier page. Sigma 1 U1 is S1, sigma 2 U2 is S2. So, suppose I have two reparameterization, sigma 1 tilde of sigma 1 and sigma 2 tilde of sigma 2. Then consider transition maps phi 1 from U1 tilde to U1 and phi 2 from U2 tilde to U2, where phi 1 as usual is given by sigma which one? Sigma 1 U1 tilde sigma 1 inverse compose sigma 1 tilde, phi 2 is sigma 2 inverse sigma 2 tilde. Then you consider sigma 2 tilde inverse compose F compose sigma 1 tilde. What I should show? I should show this map is smooth provided, so should show this is smooth provided sigma 2 tilde inverse compose F compose sigma 1 is smooth. That was a previous page, right? Okay, what's the big deal here? After all, sigma 2 tilde inverse compose F compose sigma 1 tilde, I can write it as sigma 2 tilde inverse. I can put in sigma 2 compose sigma 2 inverse, which is identity, compose F, and before sigma 1 I can put sigma 1 inverse, sigma 1 tilde inverse. These two maps are identity, right, because they are homeomorphism. So, what will happen? This is sigma 2 tilde inverse compose sigma 2 compose with sigma 2 inverse compose F compose sigma 1 compose with sigma 1 inverse compose with sigma 1 inverse tilde. Now, the transition map, we have done a theorem. Transition maps of smooth surfaces are smooth. So, these are transition maps. This is smooth, these are smooth. This is phi 1 and phi 2. This is phi 2, this is phi 1. They are smooth. This map is smooth, and composition of smooth maps are smooth. So, this map is smooth. So, whatever we have defined the concept of a smooth function between two surfaces is invariant under reparameterization. Is it clear? Just look at it once again. I will have 1 minute pause. You look at the two pages together and understand what we are going to say, that any, so our idea is whatever we define on surface, property of a surface, it has to be, the property has to be invariant under reparameterization, because if the property changes with reparameterization, then we cannot deal with the property. So, to illustrate that, we have this example wrapping the plane on the cylinder smoothly, and to make it formalize, we have done what is called a smooth map between surfaces in general, with this example in mind. And here we have shown that actually what we are saying, that these maps are, this property of these smooth maps between two surfaces, the definition is invariant under reparameterization. Now, this example we have done in the beginning, that if I have F from R2 to R, a smooth map, and I look at the level surface of his graph, I think I denoted it by GF last time. Level surface z equal to fxy. We can also consider this as changing F is equal to 0. Now, F from R3 to R. So, this is a level surface. Now, if you recall, for curves, a lecture in our last week lecture, every curve we realize as locally as level curve. So, recall every smooth curve in R2 or R3 is locally a level curve of some function R to R or R2 to R as the case may be, and this was consequence of implicit function theorem. Right, which I usually denote as IFT1 in my previous NPTEL note. If you go to the portal, you will find that there is a post on IFT1 and IFT2, implicit function theorem and inverse function theorem. On a similar vein, similarly, this is again consequence of IFT1 implicit function theorem. Proof will be posted. Don't worry too much about the proof, because that is not going to be important for the course. In this course, we want to learn certain basics about the curves and surfaces. So, this proof is not important for the course. The theorem we have here, it says that okay, locally again every surface is a level surface. So, S in R3 let for each point P in S there exists an open set in R3 containing that point and a smooth function such that S intersection W is actually the level surface for this, and for regularity purpose so this is the regularity part. Then S is a smooth or regular smooth or smooth regular surface. Okay. So, this is a direct consequence of implicit function theorem, and this is also in a way how do you construct a surface. That is, okay, I choose open sets around W, certain open sets. I construct the patches of the surface by this taking a smooth function f and look at taking a smooth function and look at the level set of that function f, and I put the patches together, then I will get a smooth regular surface. So, next time in the next lecture I will show you how torus, we have discussed about torus, the example of torus is there in the assignment also, how torus can be realized as a level surface of some smooth function f. So, that is in the next lecture. Thank you.